Okay, so today let's take the maximum minima problem to a slightly more difficult level, solving the same with a constraint or constraints for that matter. And we will in this class only focus on equality constraints. What it means is that the constraint has an equal to structure, not a greater than or a less than. For that, you need to use other techniques. The problem that I gave in the book is find the critical points of z is equal to xy such that x and y lie on x square by 8 plus y square by 2 is equal to 1. See, this is the equality constraint. So when what it means is you find in this shape, okay, this is a complex shape. Let's look at it. This is something like this is x, y is equal to, it's sort of a folded structure, z is equal to xy. Okay. And x square by 8 plus y square by 2 is equal to 1 is a ellipse. But because z is not mentioned, z can take any value. So it can go both directions of z, assuming this is x, this is y, and the top guy is z. It's sort of an ellipsoid. So what we are looking at is on that surface, this intersects it at some locations, let's say, at in those spots, which is the maximum and which is the minimum. So that is essentially what we need to find out. We use a technique called method of Lagrange parameters to solve this. So it's actually a fairly straightforward thing where we say we write a new condition h is equal to z minus lambda of x square by 8 plus y square by 2 minus 1. So essentially what we are trying to do here is instead of solving separately for xy and see whether they fall on x square or by 8 plus y square by 2, by just making this equation and solving for critical points, I'm automatically ensuring that my points lie on this curve. So now we will go ahead with what we learned in the last class. First, we'll have to find the gradient. Gradient dou h by dou x, dou h by dou y, and dou h by dou lambda also here because that constraint also has to be met. Okay, first I will take x as the variable. So this is y minus 2x by 8. This becomes 0, x by 4, y minus lambda x by 4. Now I'll take y as a variable, x minus, this becomes 0, 2y by 2, y lambda y. Dou h by dou lambda, essentially this becomes 0 and just I'll get this x square. This is essentially always it will be the constraint. Y square by 2 minus 1. And now I need to make all these three equal to 0. Y minus lambda x by 4, x minus lambda y is equal to 0, x square, this is equal to 0. So first let's do write x as x is equal to lambda y. If I make x minus lambda y is equal to 0, x is equal to lambda y. So now I substitute that x here in this value, y minus lambda times lambda y divided by 4 is equal to 0, or y minus lambda square y by 4 is equal to 0. Y gets cancelled. So y is equal to 0. Or so 1 minus lambda square by 4 is equal to 0. Lambda square is equal to 4. Lambda is equal to plus or minus 2. So we solved for lambda. Now I can use this x is equal to 2y. If I substitute lambda value here, x is equal to 2y. r minus 2y. Now I go to the constraint and I substitute that in x squared by 8. So I'll get one equation in y and I can solve it. And so when I substitute in my constraint, which is x squared by 8 plus y squared by 2 minus 1 is equal to 0, I substitute x is equal to 2y, 4y squared by 8 plus y squared by 2 minus 1 is equal to 0. This is also y squared by 2, y squared by 2. So y squared minus 1 is equal to 0, y is equal to plus or minus 1. See, whether I substitute plus 2y or minus 2y, it doesn't make a difference. I will still get 4y squared by 8. Now that I know y is equal to plus or minus 1, I know x is equal to plus or minus 2. So my final solution is x is equal to plus or minus 2, or let's do it this way. When y is equal to 1, x is equal to 2, and lambda, it didn't matter, plus or minus 2, and then minus 2 minus 1, again plus or minus 2, right? Because lambda is equal to plus or minus 2 when I substitute when I substituted in when lambda in this x is equal to plus 2y minus 2y, it didn't make a difference because the constraint had these equations squared. Right. Um, we now have the critical points 2, 1 and minus 2, minus 1. We need to figure out the Hessian to see whether the critical points are minima or maxima. So now, as usual, we will have to do what is our equation h of x y lambda is equal to xy, no, not xy. Yeah, uh, sorry, dou f by dou, I have dou h by dou x, dou h by dou y. Well, actually, we can do it like this. Um, dou h by dou x is equal to y minus, let's take lambda of plus 2, y minus 2x by 4, or y minus 2x, y minus 2x by 4, or y minus x by 2. That is dou h by dou x. So I substituted the lambda value here. Lambda is equal to plus or minus 2, right? I'm just taking plus 2 for the time being. So y minus 2x by 4, 2, x minus 2y. Dou h by dou y is x minus 2y. Dou h by dou y. So I substituted the values of lambda. Now I will need to do the Hessian, dou square h by. We know dou h by dou x, which is y minus x by 2. Dou h by dou y, which is x minus 2y. And as usual, I will do dou by dou x. I will do dou by dou y. Dou by dou x of this thing minus 1 by 2, minus 1 by 2. Dou by dou x of this thing 1. Obviously, this will be 1. This will be minus 2. Minus 1 by 2, 1, 1, minus 2. Substituting xy doesn't really make a difference. 2, 1, 1, 2, it to minus 2, minus 1 doesn't really make a difference. On the other hand, if I had taken lambda is equal to minus 2, I would have gotten um, y minus dou h by dou x, y minus of minus 2, y plus x by 4, x plus 2y, y plus x by 2, x plus 2y. So y plus x by 2, here it would have been 1, 1 by 2, and 2. Now I'll get two matrices, minus 1 by 2, 1, 1, minus 2, or 1 by 2, 1, 1, 2. Now I need to find eigenvalues and observe them. And in the you have to prompt to get the eigenvalues. Just ask ChatGPT for the eigenvalues, and once you get the eigenvalues, you are good to go. I mean, so let me see what the eigenvalues are from the textbook. Okay. Eigenvalues turn out to be in for this, it is going to be 0.85 and 2.35. 0.85 to minus 0.85, 2.35. So this is the saddle then. This is negative, this is positive, so this is the saddle. Here, interestingly, it is 0 and 2.5. And because there is a 0, we can't, this is not enough. This calculus is not enough to tell whether this point is a maxima or a minima or a saddle. So at least one point on that intersection with that constraint is a saddle point. Okay, so that is how you do the constraint. There is one more problem that I have given as a constraint, which I will with a maximum minima with a constraint, which I will do in the next video.